Polynomial functions. Polynomial functions. A polynomial function in one variable is a single term or the sum of two or more terms with variables having whole number exponents and real number coefficients. The standard form of a polynomial looks like f of x equals ax to the n plus bx to the n minus 1 plus ... plus cx plus d. So in other words, the values of a, b, c, d have to be real numbers, and the exponents, this n, n minus 1, have to be whole numbers, so 0, 1, 2, 3, 4. Standard form means that the highest power or exponent has to be first, and then we have descending exponent order as we move through each term. The degree of a polynomial is the greatest degree of any term in the polynomial. The term with the greatest degree is the leading term, and its coefficient is called the leading coefficient. The term with no variable is the constant term. So in this standard form of a polynomial, the value of d has no variable, so that is the constant term. So note that 0d would be the y-intercept. Recall, to find y-intercepts, you let x equal 0, so the only term that would be remaining is the constant term, in this case d. Let's go ahead and move on to an example. Here we have a standard form polynomial. F of x equals 3x to the fifth minus 4x squared plus x minus 2 is a polynomial with 4 terms. So terms are separated by that addition or subtraction. The degree is going to be 5, so that is the highest exponent out of all of the terms. The leading term is the term with the highest power or highest degree. So the leading term is 3x to the fifth. And the constant term is the term without a variable. So in this case, it's -2. It comes with the sign. As opposed to the function y equals 1 minus the square root of x, this is not a polynomial because it has an exponent of 1/2. And 1/2 is not a whole number. Recall that the square root of x would be x to the 1/2, and in order to have a polynomial, we need exponents that are whole numbers. In this example, we want to state the degree and write the polynomial in standard form. Then find the leading term and the constant term. In part A, we have f of x equals 5 minus pi x plus 1/3 x squared minus 2x to the fourth. So this is a polynomial. All of my exponents are whole numbers, and all of my coefficients, the numbers in front of variables here, are real numbers. The degree of this polynomial is going to be 4 because that is my largest exponent. Standard form of this polynomial is going to be rewriting so that each term is in descending power order. So standard form is going to be f of x equals -2x to the fourth plus 1/3 x squared minus pi x plus 5. The leading term, well, the leading term is the term with the degree with the highest exponent. So the leading term is -2x to the fourth. And the constant term, the one without a variable, is 5, +5. In part B, we have y equals -3x times the quantity 2x minus 1 squared. And first we want to go ahead and think about the degree. So let's go ahead and start to expand out this particular polynomial, since we'll have to write it in standard form anyways. So here we have -3x, and then the quantity 2x minus 1 squared is 2x minus 1 times 2x minus 1. Now here, if I think about 2x minus 1 times 2x minus 1, I can distribute all of that out. So I'd have that negative 3x in the front, I'd have 4x squared, and then outer and inner is going to be minus 2x, so minus 4x plus 1. But bottom line is that we would have 2x times 2x, well that's 4x squared, and then the other terms are of lesser degree, so we'd really only need to think about the 4x squared and that multiplied by the negative 3x in the front. So the degree is going to end up being a degree 3 polynomial. When I distribute in that negative 3x to each term, the highest power of x will be a 3. And we will finish distributing in the negative 3x because we do want standard form of this polynomial. So we're going to have negative 12x cubed plus 12x squared minus 3x. So that would be our standard form, writing our terms in descending power order. The leading term now we can see is negative 12x to the third, the term with the degree 3, so negative 12x to the third. And the constant term, well, the term that doesn't have any variables is just 0, because at the back here I could think about having a plus 0, so that would be my constant term. Now ideally we'd like to be able to find the degree and the leading term of a polynomial in this form, this factored form instead of standard form, without having to multiply it all out. So we'd want to be able to think about this as 2x and squared would be the highest power of x after multiplying out this 2x minus 1 quantity squared piece, and then if I multiply that by a negative 3x, that's going to give me a negative 12x cubed, making that degree 3. So that's eventually going to be kind of the goal, is we don't want to have to write it in standard form to identify the degree and the leading term. Now let's move on to talk about the graphs of polynomial functions. Polynomial functions of degree 2 or higher have graphs that are smooth, which means they have no corners or cusps, and they are continuous. And by continuous, we mean there's no holes, jumps, or breaks in the graph. So in this example, the question is, could the graph shown represent a polynomial function? If not, explain why. In our first graph, we have an absolute value function that's reflected over the x-axis and shifted left 2. So we have a corner to our function at negative 2. So this could not represent a polynomial function, so the answer is no. And the reason is because there is a corner at x equals negative 2. The second example here, we do have a smooth graph, so we don't have any corners or cusps, which are basically sharp turns. We have these nice smooth turns. And we are continuous, so I can draw this particular graph without ever lifting up my pencil. There's no holes, jumps, or breaks in the graph. So the answer here is yes, this could represent a polynomial function. Finally, this last example, I have these 3 pieces to my function, and they're separated by vertical asymptotes at negative 3 and at 2. So this could not represent a polynomial function. The answer here is no, and that's because I am discontinuous. So I am discontinuous at 2 different places actually, at x equals negative 3 and at x equals 2. Now we're going to look at a specific type of function called a power function. A power function is of the form f of x equals a times x to the n. So now we're going to look at some examples of power functions that are polynomials. So the function f of x equals x to the first power, well that's of the form ax to the n. I have 1x to the first power. That is a power function, which we know represents a line that passes through the origin with slope 1. So this is a linear function. We can also look at the power function f of x equals x squared, which we know is a parabola when we graph it, and we call this type of function a quadratic function. Moving on, we can think about the power function f of x equals x to the third. So f of x equals x to the third was one of our basic functions. We know that it is continuous and it lives in quadrants 1 and 3 and passes through the origin. And we call this power function a cubic function. Finally, we're going to go ahead and look at the two power functions f of x equals x to the fourth and f of x equals x to the fifth, and kind of establish some relationships between these power functions and the ones previous that have lesser powers. So f of x equals x to the fourth, that would be considered a quartic function. And its graph is similar to the graph of x squared. It still is a U shape, but it's a more flattened out U. So notice it also passes through the points 1, 1 and negative 1, 1, because if we plug in 1, 1 to the fourth is 1, negative 1 to the fourth is 1, just like x squared passes through 1, 1 and negative 1, 1. But the graph of x squared we call a parabola, and that's a very specific name for a quadratic function's graph. A quartic function just has a U shape, but it's not considered a parabola because it actually flattens out more in between that negative 1 and 1. So it's closer to the x-axis for more values between negative 1 and 1. And for the graph of x to the fifth, so that's a quintic function, and it's pretty similar to a cubic, a degree 3, in that it passes through 1, 1 and negative 1, negative 1, because again, if we substitute in those values into x to the fifth, those are the y values that will come out, just like x cubed. But it also is more flattened out between negative 1 and 1. And the reason for that flattening out as we increase the power is because essentially as we're plugging in fractions, those are the values that live between negative 1 and 1, so fractions like 1/2 or 3/4, if we raise those to a power like 5 or 4, it actually makes those numbers even smaller. So if I had something like 1/2 to the fifth, that's going to be 1 over 32, versus 1/2 to the third, that's 1 over 8. So 1 over 32 is much smaller, so that's why we have this flattening out happening the higher power that we have on these types of power functions. So the pattern I kind of want you to start to recognize is when I have an even degree on these power functions, they look pretty similar. They have this sort of U shape, but really what I want you to focus on is that both ends of the function are going towards positive infinity. Versus if I have an odd power degree function, so x to the 1, x to the third, x to the fifth, now the end behavior, so towards the right and the left side of each of these functions, they're going opposite. So instead of both going up, like x squared and x to the fourth, for all the odd power functions, one side's heading up and the other side is heading down. In fact, the right side's heading up and the left side is heading down. So that's just some patterns I want you to recognize as you observe these power functions. Just a quick note, we were looking at power functions that were polynomials because they have whole number exponents, but note that the square root of x, which is of course x to the 1/2, that would also be considered a power function. So would 1 over x squared, because we could rewrite that as x to the negative 2. So these are also power functions, but we specifically were thinking about power functions that are polynomials. In this review example, we're going to use transformations to graph y equals negative 1/2 times the quantity x plus 2 to the fourth minus 1. So the only part that's really new here is that our parent function is x to the fourth. So we're going to identify the parent function as x to the fourth, and let's identify the transformations. The negative in the front is going to reflect over the x-axis. The 1/2 that's multiplied in the front is going to give us a vertical compression by 1/2. And then finally, we have our translations. So plus 2 inside with the x is going to move us left 2, and minus 1 on the outside is going to move us down 1. So we have left 2 and down 1. So let's go ahead and apply these transformations then. So our parent function, we'll start by sketching our parent function. So it passes through 0, 0, 1, 1, negative 1, 1, as we said. And I'm going to go ahead and sketch it, and I'm going to emphasize that it really flattens out on the bottom there. So this is going to be my function x to the 4th. Now, if I want to do the vertical compression next, I'm going to affect the y value since I'm a vertical compression. So instead of 1, 1, this coordinate point would be 1, 1/2. So I'd have 1, 1/2, negative 1, 1/2. And then I would go ahead and sketch that. Kind of looks like it's running into each other a little bit. So this is 1/2 x to the 4th. It doesn't intersect, it kind of just looks like it does there. And then we're going to reflect it over the x-axis next. So our reflection over the x-axis, we're going to still pass through 0, 0. Now it won't be so cluttered. We're going to have 1, negative 1/2, negative 1, negative 1/2. And then again, I'm going to try to make it look like it flattens out more near the x-axis. And then we'll move everything left 2 and down 1. So we're going to go ahead and move our vertex negative 2 and then down 1. So negative 2, negative 1, and then we'll have our other coordinate points that are just a half unit away below it. And then we'll go ahead and connect those, again trying to make it look a little flatter on the bottom. So this is going to be our final graph here of y equals negative 1/2 x plus 2 to the 4th minus 1. And then we'll label this was negative 1/2 x to the 4th. So very similar to what we did with our other parent function. So now we're just trying to identify this new parent function x to the 4th, which is a little bit more flattened out. And we just want to do our best to emphasize how it really does flatten out more than the graph of x squared. So in our last example, we graphed a higher degree polynomial, a quartic polynomial, using shifts in the graph and transformations. But what if we have a higher degree polynomial in standard form? That whole ax to the n plus bx to the n minus 1, etc. How would we graph something that looks like that? Well, we're going to kind of break that apart into pieces. So we're going to start by determining what we call the end behavior for a polynomial function that looks like y equals ax to the n plus ... plus a bunch of terms. And we don't really care what those other terms are because we're going to determine this end behavior using the leading coefficient test. So the leading coefficient test is first going to have us think about the degree of the polynomial, whether the degree is even or odd. So if I have an even degree polynomial, so n in this case is even, then there's two possibilities at that point for the value of a being the leading coefficient. A could either be greater than 0, meaning a is positive, or a could be less than 0, meaning a is a negative value. So my tip for this is to think back to our familiar function y equals x squared. This is an even degree with a positive leading coefficient. The leading coefficient is 1. So if we want to describe its end behavior, well, the ends of x squared are both pointing up. So the right side is pointing up and the left side is pointing up. So those are the only parts we want to think about in terms of x squared are the ends, because we don't know what happens in the middle. So I'm kind of just going to put like a wavy dotted line because we don't know what happens in the middle. So in general, if I have an even degree with a positive leading coefficient, the left side and the right side point up. Now if I have a negative leading coefficient, then I would think about instead y equals negative x squared. And a negative in front of a function reflects over the x-axis, so both sides would be pointing down in terms of end behavior. The left side points down and the right side points down. And again, we don't know what happens in the middle. So to describe what is happening using an alternate notation, what we're saying is that as x values are going towards positive infinity, so positive infinity on the x-axis, f of x values, those are y values are going to positive infinity. And as x values are going towards negative infinity, what is happening to f of x? F of x is still going to positive infinity. And when I have a negative leading coefficient, as x goes to positive infinity, my y values, f of x, are going to negative infinity. And as x goes to negative infinity, my y values, my f of x values, are going down to negative infinity. The other possibility is if I have an odd degree leading term. So in other words, if n is odd. And then we have the two choices of a, the leading coefficient, to be positive or negative. So my tip here is to think about y equals x cubed, or really any odd degree power function that we are already familiar with. So we should be familiar with x cubed. And the end behavior is that the right side towards positive infinity points up. So as x goes to infinity, y values f of x goes to positive infinity. And the left side points down. So as x values go to negative infinity, the y values go towards negative infinity. And we don't really know what happens exactly in the middle. In general, we know what happens in the middle of x cubed. But for any odd degree polynomial with a positive leading coefficient, the right side points up and the left side points down. And if a, that leading coefficient, is negative, then of course we reflect it. So the left side points up and the right side points down. So as x goes to positive infinity, the y values go to negative infinity, f of x, and as f of x goes to, or as x, goes to negative infinity, f of x goes to positive infinity. So I like to think about it as if I have an odd degree, odd goes the opposite direction. So it's just a matter of the leading coefficient being positive, the right side goes up, the left side goes down. If the leading coefficient is negative, then the left side points up and the right side points down. But if it feels like a lot to memorize, always just go back to x squared and x cubed, because those are parent functions that we should already have memorized. In this example, we're going to use the leading coefficient test to determine the end behavior of the graph of the given polynomial function. Sketch it and describe it at the ends of the function. So here first we have f of x equals 10 minus x minus 5x to the fourth. So we'll start by identifying the leading term. The leading term tells us both the degree and the leading coefficient. So our degree is 4, which is even. So we know that either both sides point up or both sides point down. Well, the leading coefficient is negative 5. So since the leading coefficient is negative, both sides point down. So we can relate this, we can think about like negative x squared. So because it's even and I have a negative leading coefficient. So both sides are going to point down. So this is a sketch of the end behavior. And again, we don't know what happens in the middle. And to describe what happens as x goes to positive infinity, as x goes to the right, my y values go down to negative infinity. And as x values go towards negative infinity, again, my y values go down to negative infinity. In the next example, we're going to have to do a little bit more to think about the degree and the leading coefficient. I have negative 3x cubed times the quantity 2x minus 3 squared. So this is not in standard form. So in order to think about the degree, I'd have to think about what would happen if I multiplied it all out without actually multiplying it all out. So 2x minus 3 squared, well, that would end up being 4x squared, and then I'd have some other terms. But that 4x squared would be the highest term for that distribution, and when I think about multiplying 4x squared times negative 3x cubed, I'm going to end up with a degree 5 overall. So my degree is going to be a degree 5, and that's an odd power. And then my leading coefficient, well, that would end up being negative. I had 2 squared, that 2x squared, that was 4x squared. And then I have this negative 3. So my leading coefficient would actually be negative 12. So if I have an odd degree, odd means opposite, they point opposite directions, and a negative leading coefficient means that we would think about x cubed, but then flip it. So instead of the right side going up, the left side goes up and the right side goes down. And we don't know what happens in the middle. So that's a sketch. And now to describe it, well, as x goes to infinity, as I move to the right, my y values go down to negative infinity. And as x values go towards negative infinity to the left, my y values go up to positive infinity. And in our last example, we have f of x equals 3x squared times the quantity x plus 2 squared times the quantity x minus 1 squared. We definitely don't want to have to multiply all this out and write it in standard form to find the degree. We'd simply want to think about that each of these binomials, x plus 2, x minus 1, each squared, would give us an x squared and an x squared, and that would multiply to this 3x squared in front. So that would mean that the degree overall is going to be a degree 6. So x squared, x squared, x squared, all multiplied out would be x to the 6th, which is even. And then my leading coefficient this time would be just 3, because there was just 1s in front of each of these x's. So I have this 3 in front that would multiply to those 1s. So I have a positive leading coefficient. So we can basically just think about x squared, right, an even degree with a positive leading coefficient. So the right side points up and the left side points up. As x goes to both positive infinity and negative infinity, the y values, f of x, goes up to positive infinity. Now that we've covered the end behavior of the graph, we want to think about real zeros and their connection to the graph. So if I have a function, f, and r is a real number for which f of r equals 0, then r is called a real zero of f. Now we're going to talk about these zeros and what are called their multiplicities. So let's say we're given a polynomial, f of x equals a times the quantity x minus b to the n times the quantity x minus c to the m times the quantity x minus d to the k. Here this is a polynomial, but not in standard form. Well, since it's factored, x minus b as a quantity, quantity x minus c, and quantity x minus d are all called factors of f of x. And therefore b, c, and d are solutions to the equation f of x equals 0. Now, these solutions, b, c, and d, are again called real zeros. We just defined that above, but they are real zeros of multiplicities n, m, and k respectively. So b is a real zero from this factor, and because the power there is n, we say that b is a real zero of multiplicity n, c is a zero of multiplicity m, and d is a zero of multiplicity k. And any solution, any real number solution to the equation is an x-intercept. So b comma 0, c comma 0, d comma 0 are all x-intercepts of the graph of f of x. In this example, we want to form a polynomial function given the following information. Assume all zeros have multiplicity 1 unless otherwise stated. So we want to form a polynomial in part A with zeros, -2, 0, 1, and 4, but 4 has a multiplicity of 2. And this has to be a degree 5 polynomial. So what we're going to do is start out by saying f of x is equal to, well, if -2 is a 0, then x minus -2 is a factor. And we assume it's to the first power because all multiplicities are 1 unless otherwise stated. If 0 is a 0, then the factor x minus 0 has to be included in our polynomial. And again, with a multiplicity of 1. If 1 is a 0, then x minus 1, again, to the power of 1, has to be a factor. And then lastly, to have 4 as a factor with a multiplicity of 2, we need a factor that looks like x minus 4 as a quantity squared. And if I simplify this a little bit, or at least clean it up a little bit, I'm going to put that x minus 0 to the first in front, so that's just x. And then I'll put x plus 2 from x minus -2. Then the factor x minus 1, followed by the factor x minus 4 squared. So if we multiply this all out, which we won't, we don't have to, we can tell just by looking this is a degree 5 polynomial. I have x to the first, x to the first, x to the first, and here it would be x squared. So altogether I have x to the 5th would be my degree. And then in part B, we have to create a polynomial with zeros, -1, 1, and 3. So we just assume they're all multiplicity 1, and this polynomial needs to have degree 3 overall. So we're looking at f of x equals x, and then we'd have minus -1, so we want to be able to jump straight to x plus 1. And then our other factors will be x minus 1, and x minus 3 to ensure that we get the zeros of 1 and 3, all with multiplicity 1. And if we did multiply this all out, we would have a degree 3. We'd have x cubed if I went through the process of all the distribution. Let's talk about the behavior at the x-intercepts near the x-axis. So if the quantity ax minus b in parentheses raised to the r power, if that is a factor of f of x, then what we know is b over a is a 0, so we're getting that because we would add b and divide by a to the other side. Then b over a is called a 0 of multiplicity r, because that is the power of the factor. Now, depending on r, different things will happen at that x-intercept. So b over a will be a 0, or an x-intercept, and on the graph, depending on the multiplicity, different things will happen. So if r is even, so if the exponent, the power of the factor is even, then at the x-intercept, at b over a, 0, the graph bounces off of the x-axis. So over here, here's just a random polynomial graph, and this right here describes a bounce. So we're just kind of tapping the x-axis and then staying on the same side of the x-axis. So in other words, this particular polynomial, at this particular 0 or x-intercept, -2, it came from a factor that was even. So since the 0 is -2, the factor would have to be x plus 2. So the factor that -2 came from is x plus 2, and because the graph bounces there, it would have to have an even multiplicity. So it doesn't necessarily have to be 2, but it has to be an even multiplicity. Now, if r is 1, so if the factor only occurs one time, then at the x-intercept, at b over a, 0, the graph just crosses through the x-axis. So over here, this is what we mean by just sort of crosses through the x-axis. So that happens at -4. So that means that the factor that this came from, So the factor would have to be x plus 4 to give you a 0 that is negative 4, because I'd have to subtract 4 to the other side. This had to come from a factor raised to the first power. So then finally, we have if r is odd and r is greater than 1. So now if the multiplicity r is an odd number, but it has to be bigger than 1, so 3, 5, 7, then at that x-intercept, b over a comma 0, the graph crosses tangentially through the x-axis. So it's still going to go through the x-axis, but it's going to sort of flatten out a little bit. So this 0, 2, had to have come from the factor x minus 2. That's how you'd get out positive 2 as a 0. So because it sort of flattens out, it's crossing tangentially, the multiplicity would have to be an odd number greater than 1. So let's just go ahead and make it 3. So this is a possibility, multiplying these together, right? These would be factors, so they'd have to be multiplied. This is a possibility for this function. So this function might be quantity x plus 4, quantity x plus 2 squared, and quantity x minus 2 cubed. Now, the way I like to remember this is if you know your basic functions, we know that the function, so I'm just going to kind of write it up here, we know that the function y equals x, well that's x to the first. What does that do? Well, that just crosses straight through the x-axis. And what do we know about y equals x squared? Well, the multiplicity there is 2, and what happens is it just bounces off at 0. And then y equals x cubed, well, if we know the graph of that basic function, it flattens out. I didn't do a good job right there, but it flattens out at 0 because its multiplicity is 3. So a lot of people are like, oh, this is a lot to memorize, but if you know the graph of your basic functions, it follows the same behavior, but just at different values at the different x-intercepts. Now the last part is if f is a polynomial of degree n, so if the degree of the entire polynomial is n, then the graph of f has at most n minus 1 turning points, or we call those local extrema. So if the polynomial has a degree n, there's one less than that, at most, turning points. So this graph right here shown has 3 turning points. So we're talking about local extrema. So there's a local min here, a local max here, and a local min right here. Remember, this is nothing, right? This just continues to increase. So this particular polynomial has 3 turns. So it might be a degree 4 polynomial or higher than that, because if it was a degree 4, then the most amount of terms it can have is 4 minus 1, so 3. But it could also be degree 6, because that's still less than 5. 3 is still less than 5. So the graph has at most n minus 1 turns to it. All right, let's put all of this together in an example. So we want a graph f of x equals 2 times the quantity x plus radical 2 times the quantity x minus 2 squared. Now here are the steps. The steps for graphing a polynomial function provided we are in factored form, which this is completely factored. We want to determine and sketch the end behavior. So here, we'll go ahead and just call it like step 1 to match the steps here. The end behavior is based on the degree. So here, this is x to the first. This is going to be x squared. So the total degree is going to be x cubed, like if I multiplied it all out. And the leading coefficient of that leading term is going to be 2 if I multiply everything out. So my leading term is going to be 2x cubed. So if I have a odd degree with a positive leading coefficient, I should just think about the regular graph of x cubed. Well, the right side points up and the left side points down. We don't exactly know what happens in the middle yet with this graph, but we're just describing the end behavior. Step 2, find the real zeros, their multiplicities, and behavior near the x-axis. So what we're going to do is create a little table to organize our thoughts here. So the real zeros, so I'm going to go ahead and put the zeros, their corresponding multiplicities, and then their behavior near the x-axis. So 2, this doesn't have any x's with it, so that's not going to give me any zeros. So here, x plus radical 2. So one of the real zeros will be negative radical 2, because remember, I would set this factor equal to 0. We should be able to do that in our head. The multiplicity is 1. So the behavior near the x-axis is that it's going to cut through the x-axis. So if the multiplicity of the power is 1, it's going to act just like y equals x. So it's going to cut through the x-axis, right? So you can write the word cut, or maybe just draw like a little line to remember it's just going to go straight through. The second zero is going to be positive 2. If I set x minus 2, if I set the factor equal to 0, I'll get positive 2. The multiplicity is 2, which is the power of the factor. And if the multiplicity is 2, then we're going to have to bounce off the x-axis. So I could either bounce up or bounce down. With cutting, I can either cut, with the positive or like a negative sloped line. So we, again, write the word, or you can think about the graph. And now we're going to go ahead and start to put all of this together. So we want to plot the x-intercepts and the y-intercept. So remember, to find a y-intercept, we set x equal to 0. We really already have the x-intercept. So for part 3, the x-intercepts are going to be negative rad 2, 0, and 2, 0. So that's the real zeros. Those are x-intercepts. The y-intercept, we would have to plug 0 into these x's. So to find the y-intercept, f of 0, that's 2 times rad 2 times 4. If I plug in a 0 here, negative 2 squared is 4. So I have 8 radical 2. So my y-intercept is 0, 8 radical 2. All right, so let's go ahead and start by plotting those values. So we have negative radical 2, and so that's a little bit more negative than negative 1. So I'm going to go ahead and plot it right here, negative radical 2. And one of the things I like to do is remind myself what's going to happen there. So I'm going to cut the x-axis there. So what I'm going to do is put a little c to remind myself what's going to happen there. I'm going to cut there. My other x-intercept is 2, 0. So I'm going to go ahead and plot that, make it a little bigger. That's a 2. And my behavior there was I was going to bounce, so I'm going to put like a little b to remind me what happens there. And my y-intercept is 0, 8 radical 2. So notice the y-axis isn't labeled. So we can just, that's a positive number. So it's not going to be to scale. We're just going to go ahead and label this up here as 8 radical 2. So we plot the x-intercepts, the y-intercept, and then we're going to sketch with all the behavior. So we only sketch the end behavior over off to the side. Well, I want to go ahead and sketch the end behavior on the graph. It's going to point up and to the right, and I want to be sure to be on the right-hand side of any x-intercepts. And then it's going to fall down into the left. So it's going to go ahead and fall down here. So now I want to go ahead and sort of put it all together. I like to go ahead and start from left to right. I'm going to pick up at my end behavior, and I'm going to head towards my graph, or towards my x-axis, knowing that I'm going to have to cut through the x-axis, and then I have to go through my y-intercept. Now, I don't know exactly what the graph's going to look like. I just know that I have to go through this point up here. So I'm going to give you some options. Some people want that to be the highest point. You can do that. That's fine. You could also sort of go straight up here and curve back down. I'm going to start over again because it's starting to look ugly. I'm going to say this goes down. It can go up and go like that. So it can go a little higher on the left. It can go a little higher on the right. We're just not quite sure. So I'm going to go ahead and go a little higher here and then come back down. And then I know that I have to bounce off of the x-axis at 2 and then pick up where I left off. So I kind of went ahead and did it a couple times to make it look nice because it's supposed to be a smooth, continuous function. It shouldn't have any sharp corners. These should be nice, like rounded out peaks and valleys to be a polynomial. So we cut at negative radical 2, we bounced at 2, we passed through in some way our y-intercept. So again, that could have been the highest point. We don't know exactly how high we go. We would need calculus for that. Now the last part is just a check. Verify the graph is a function, and it is, and check the maximum number of turning points. So this degree, we said the leading term was 2x cubed, so I'm going to go ahead and say like part 5. The degree of the polynomial was 3. So that means, that implies that the maximum number of turns that it could have is 2. That's the most it could have. It doesn't have to have 2, that's the most. Well, it has 2. There's a local maximum here and a local minimum here. So max number of 2, like check. So this is just to make sure we didn't do anything crazy and we satisfied the most amount of turns it could have, or that it didn't go over the most amount of turns. All right, let's go ahead and graph another one of these. So we have negative 1/2 x times the quantity x plus 2 times x minus 4 squared. So we want to start with the, finding the end behavior. So we need the degree, or we need the leading term really. So the leading term here is going to end up being negative 1/2. If I multiply all the x's, I'm going to have a coefficient of negative 1/2. So leading term is going to be negative 1/2, and then x raised to the 4th power. So I have x to the first here, x plus 2 to the first here, and then here x squared. So if I multiplied it all out, I'd get an x to the 4th. Well, if I have an even degree and a negative leading coefficient, think about negative x squared. It's going to have my end behavior pointing down on both sides, and I'm not quite sure what's happening in the middle yet. Now we move on to finding the zeros and their multiplicities and their behavior. So we're going to put, I'm going to make a little table, I'm going to shorten it, the zeros, the multiplicity, and the behavior near the x-axis. So I'll put behavior x-axis. So the first 0 this time is actually 0. So I have an x out here. On the last one I just had the number 2. Here I have a negative 1/2 x, or another way to think about it is this is like x minus 0 to the first. So the 0 here is 0. So here I'm going to start with 0. The multiplicity is 1, and it's going to have to cut through the x-axis. From the second factor with x in it, I have x plus 2, so the 0 would be negative 2, if I set that equal to 0. Negative 2, multiplicity, the power of that factor is 1, so I'm going to cut the x-axis. And x minus 4 will lead to a 0, a real 0 of 4. The multiplicity is 2, and it's going to bounce off the x-axis because that's an even number. Now let's go ahead and identify the y-intercept. I mean, this is all just kind of scratch work for us here. So we know these zeros are also x-intercepts because they are real zeros. So to find the y-intercept, we're going to let x equal 0. Well, if I let x equal 0, if I do f of 0, I'm going to get negative 1/2 times 0. And then, I mean, it is 2 to the first and then negative 4 squared, but it doesn't really matter. 0 times anything is 0. So my y-intercept is 0, 0, which makes sense because I have an x-intercept that is 0. And then now let's go ahead and plot all of this. Let's go ahead and plot the x-intercepts first. That's what I always start with. So the x-intercept of 0, what happens there is I'm going to cut, so I'm going to put a little c. Negative 2, I'm going to cut there, so I'm going to put a little c. At 4, I'm going to bounce, so I'm going to put a little b. And then that is already plotting the y-intercept. And now we are going to go ahead and graph the end behavior. So the right side is going to go down. So I'm going to start just barely on the right of negative 2, and on the left of negative 2, excuse me, and then on the right of 4, so my end behavior is going down. And then let's go ahead and start on the left-hand side, pick up where you left off, and make sure we're following the x-axis behavior. So at -2 we're going to cut, so I'm going to pick up and just cut through. And then again, we don't know how high we go here. So we do know we're going to have to turn because we have to cut through 0. So I'll just go a little bit higher up, and then I'm going to turn myself and cut through 0. And then we're going to have to go over here and bounce off of 4. So I'm going to have to turn again to bounce off at 4. So I'm going to turn here, nice and smooth, bounce off of 4, and then go back down. So try to round this out a little bit. So here is my graph, a sketch of my graph, because I don't know quite how high this goes or how low this goes, but I do know this is the general shape. And let's just check the maximum number of turning points. Well, the degree was 4, so that means the max number of turns, the most it can have, the max number of turns is 1 less than that, so 3. And this has 3 turns. So this is a turn, this is a turn, and this is a turn. So it satisfies it has the maximum number. It could have had 2, 1, or 0, but it satisfies the maximum number of turns. In this example, we want to graph -x squared times the quantity 2x minus 7 squared times the quantity x squared plus 1 times the quantity x plus 5 cubed. So let's start by finding the leading term. So here we have -x squared, and here we have 2x minus 7 squared. So this 2x would get squared, and that would mean I'd have a 4x squared times this -1. So I'm going to have a leading coefficient of -4. So the leading term will have a leading coefficient of -4. And then let's think about all the x's. So x squared, here we're going to have an x squared, so that's x to the 4th. We have another x squared, that's x to the 6th. And then x to the 3rd, so we're going to have x to the 9th. -4x to the 9th. So we have an odd power. So odd means opposite. So we're going to have opposite end behavior. And then negative is going to flip it so that the left side points up and then the right side points down. So we're like thinking about flipping x cubed. An odd power, but with a negative in front, would flip it. Now, in terms of the zeros, we're going to think about the zeros, their multiplicity, their x-axis behavior. So the first 0 is going to be 0 from this x squared term. So 0 with a multiplicity of 2, therefore it will bounce off the x-axis. The next factor, 2x minus 7, is going to give us a 0 of 7 over 2. So we have 2x minus 7. If I set that equal to 0, I'm going to get 2x equals 7, or x equals 7 over 2. Now we should be able to quickly do that in our head. I just wanted to show that because a common mistake is just to take the opposite of this number. So people just put, oh, 7. But we have to add 7 and divide by 2 to find the 0. The multiplicity is 2, and it is again going to bounce. Now this next factor, x squared plus 1, this can't be factored any further because this is a sum of squares, and it's actually not going to give us any real zeros. So if I tried to set x squared plus 1 equal to 0, I get x squared equals -1, or x equals plus or minus I, because I would take the square root of -1, and that would give me an imaginary number. So this isn't going to give me any real zeros, because I'm interested in zeros that are x-intercepts. But the last factor, x plus 5, will give me a 0, or an x-intercept, of -5 with a multiplicity of 3. And because the multiplicity is 3, we have to say it cuts tangentially. So we cannot just put cuts. At the very least, we have to put cuts tan, because it's going to flatten out. Alright, and then we need the y-intercept. Well, the y-intercept is going to be 0, 0. We already know that because we know an x-intercept is at 0. And let's also just talk about the maximum number of turns. So since the degree is 9 of this polynomial, that means that the maximum number of turns is 1 less than that. So the most it can turn is 8 times. All right, let's go ahead and graph all this. So the x-intercepts first, so I like to start with that. We have 0 as an x-intercept. If the multiplicity is 2, it bounces. 7 over 2, well 7 over 2 is 3.5. 2 goes into 7 3.5 times, so we have 3.5 over here, that's 7 over 2, where it is also going to bounce. And we have -5 way over here where it's going to cut tangentially. So I'm going to put a little CT there for cuts tangentially. And then, doesn't quite look like a 5. I'm going to put, it did it again. Make sure it did. I'm going to go ahead and do the end behavior. So to the left of -5, I'm going to point up. To the right of 7 over 2, I'm going to point down. So I like to just get kind of close. And then let's go ahead and do it. So I'm going to cut tangentially here. So as I approach, I'm going to flatten out near the x-axis. So I don't just want to cut, I want to flatten out and make it very clear that that's what I'm doing. And then I'm going to have to turn around if I bounce off at 0. And then I have to bounce off at 7 over 2 and connect to my other end behavior. So this is a sketch. Again, we don't know how low these little local minimums go. It's just a sketch. But let's count the turns. So we have 1, 2, 3, 4 turns. So we only had 4 turns this time, but that's fine because as long as I didn't have more than 8. The maximum number of turns is 8. In the following examples, we want to determine if the graph shown could represent a polynomial function. If so, construct a polynomial function for it with the smallest degree possible. If it's not, explain why not. So in this first graph, this could represent a polynomial function because it's continuous and smooth. It doesn't have any sharp turns. So to construct the polynomial function, what we need are the zeros, and to analyze the behavior near the x-axis at those zeros, at those x-intercepts, and to think about the end behavior and the y-intercept. So let's start with the x-intercepts. So here -1 is an x-intercept, so that means that the factor that it comes from would be x plus 1, and because it just cuts through the x-axis there, its multiplicity would be 1. Then we have 0 is an x-intercept, so the factor it comes from is formally x minus 0, or just x, and it also cuts through the x-axis, so the multiplicity would be 1. And then 4 is a 0, or x-intercept, but it bounces off the x-axis, so when we create its factor, it's going to be x minus 4, and then it's going to have to be an even power, but we want to do this with the smallest degree possible. So we're going to put 2 for the multiplicity of the factor x minus 4. So now we just want to make sure that we have satisfied the end behavior. So here, this polynomial, if I multiplied it all out, it would be x, and x squared, so x to the 4th. Well, it would be positive x to the 4th, and these ends are pointing down, so we would need a negative leading coefficient. So here I'm going to go ahead and call this function f of x, so this is some function f of x, and I'm just going to multiply it by a negative in the front. And I want to make sure now also that the y-intercept is satisfied. So the y-intercept is 0, 0. And that is satisfied by this x term right here. So to make it look a little bit nicer, it would look like negative. I'm going to put the x first, then x plus 1, then x minus 4 squared. So we usually put the individual variable x, which came from this middle factor, in front, and then x plus 1, and then x minus 4 squared. So the negative needed to be multiplied to the front because it satisfies the end behavior. And the y-intercept is satisfied, because if I plug in 0 here, I will get out a 0. Now looking at the next graph, this too represents a polynomial function because it is continuous and smooth. There's no sharp turns. So let's go ahead and think about what its equation might look like. We'll start with the x-intercepts. So we have -3 as an x-intercept. So that comes from a factor of x plus 3 with a multiplicity of 2 because it bounces and we want to pick the smallest degree. So 2 is the smallest even degree. The second 0 is at 2 where it just cuts. So we're going to have x minus 2 to the first power. So I'm not even going to write anything there because we know that it's implied a 1 if we don't. And let's go ahead and check the end behavior right now. So the end behavior, the right side is pointing up, the left side is pointing down. If I look at what I've created so far, I have x squared and x, so a total of x cubed. Well, positive x cubed does have the right side point up and the left side point down, so the end behavior is satisfied. So we have the x-intercepts are satisfied by these factors. These factors also happened to satisfy the end behavior without having to do anything like multiply by a negative to flip things. But there's one last piece here, the y-intercept. So the y-intercept needs to be -6. So let's check right now what we have. So we have f of x is currently x plus 3 squared times x minus 2. So let's see what happens when I plug in 0 into that. So what is f of 0? Well, that's 0 plus 3 squared, so 3 squared, times 0 minus 2, so times -2. So we end up with, negative 18. 3 squared is 9, 9 times -2 is -18. We don't want -18 as the y-intercept. We want -6, which is 1/3 of -18. So the only thing that we are allowed to do right now, we can't, we don't want to add any additional linear factors because that's going to give us some more zeros. Right? We don't want any more zeros, so we want to stick with this idea of multiplying in the front by a coefficient. So what we need to go ahead and do is I'm going to move this over. We need to think about, well, what coefficient do I want to go ahead and multiply in the front so that I can make my current y-intercept, -18, into -6? Well, I want to multiply by 1/3. I want to multiply by a 1/3 in the front. Let me erase that, highlight. Because now what that'll do, so now that's not my function. My function at 0 would be 1/3 times 3 squared times -2. So 1/3 times 9 times -2, that's 3 times -2, or -6. So we want to go ahead and multiply by a different coefficient in the front to make sure we satisfy that y-intercept. Now let's go ahead and talk about solving polynomial inequalities. In this first example, we want to solve 8x minus 27 is less than 2x cubed minus 3x squared by graphing. Well, these are going to work a lot like quadratic inequalities, where we do want everything on one side and a 0 on the other side. So I'm going to go ahead and subtract the 18x and add the 27 to the other side. So I'm solving 0 is less than 2x cubed minus 3x squared minus 18x plus 27. And that was just to keep a positive leading term here, positive leading coefficient. But if we want the 0 to be on the other side, then what we'd have to do is think about it as 2x cubed minus 3x squared minus 18x plus 27. When is that greater than 0? Right, so we want the inequality, the shark mouth to be eating the 2x cubed part. So we have to flip it if we want it to be on the left-hand side. All right, so in order to graph it, we need to have it factored. So 2x cubed minus 3x squared minus 18x plus 27, how do we factor that? Well, it has 4 terms, so we want to factor by grouping. So we're going to create our 2 groups, and we're going to factor out an x squared. So we're left with 2x minus 3. And then here we'll factor out a -9, and we are left with 2x minus 3. And so we have the same factor in each term that we're going to pull out. So we have 2x minus 3 times what's left over from the first term is x squared minus 9 is left over from the second term. So review of factoring by grouping. But x squared minus 9 is the difference of squares. So we have to factor completely. So we have 2x minus 3 times x plus 3 times x minus 3. Alright, so now that it's fully factored, we know how to graph it from our previous steps above. So what we want to do is ultimately find the end behavior, the zeros of the function, and that's really all we need. We don't need the y-intercept. We really just need the x-intercepts and the end behavior for the general form. So here I'm going to go ahead and kind of do this in a different way, or slightly different notation in my work, because this is all just scratch work for me. So I know that my 0 here is going to be 3 over 2 with a multiplicity of 1. And then I'm going to have it's a 1, negative 3 again with a multiplicity of 1, and then a positive 3 again with a multiplicity of 1. So I have 3 over 2, and it's going to cut. I'm going to have negative 3, and it's going to cut, and I'm going to have positive 3, and it's going to cut. And then my leading term, well, let's not work with the factored version. Let's just go ahead and look back at the standard form of the polynomial, 2x cubed. So the end behavior is that the right side points up and the left side points down, like regular x cubed. That's positive. So again, we're not concerned with the y-intercept. We don't have to really care about it, although it is pretty easy to find because we have standard form. So if I let all these x's be 0, the y-intercept is 27. So it's like way up here. Let's fake it and say this is 27 up here as the y-intercept. So here we're going to pick up where we left off. We'll cut. We'll come up here. We'll cut, and connect, right? So we're going to cut through all 3 x-intercepts and then match our end behavior. So what we are looking for is where is this polynomial greater than 0? So if I do this by graphing, the way that I want to think about it is where am I above the x-axis, right? Greater than 0 is above the x-axis. So if we kind of highlight those regions, I'm above the x-axis between these two x-intercepts, negative 3 and 3 over 2, and I'm above the x-axis beyond this x-intercept of 3. So that's why we really need the x-intercepts. That's where we can possibly change from above to below the x-axis. So let's describe these intervals. That would be from negative 3 to 3 over 2, open, when I'm greater than, not greater than or equal to, and positive 3 to infinity. In this example, we'll solve quantity x minus 3 times quantity x plus 4 squared times quantity 1 minus x greater than or equal to 0 algebraically by creating a sign chart. So algebraically means by creating a sign chart as opposed to doing a graph. Well, thankfully this is already in factored form. So what we need to do is set this equal to 0. So again, similar to quadratics, what we need is the zeros, but since it's already factored, x minus 3, x plus 4 squared, 1 minus x equals 0, we can easily find all of the zeros. We get x equals 3, x equals negative 4, and here we'd get x equals 1. So what's the value that will make 1 minus x equal 0? Well, positive 1. So these are my zeros. So in the same way you'd find them to graph them, we're going to find them, but to put them on a number line. So we're going to go ahead and graph our number line. And the domain of any polynomial is all real numbers. So our number line will have negative infinity to infinity. And we'll plot our zeros. Negative 4 is a 0. We have positive 1 is a 0. and positive 3 is a 0. And then we go ahead and we are interested in, again, what's happening over each interval. So what's happening sign-wise, like is it positive or negative, when I'm between negative infinity and negative 4, or between negative 4 and 1. So instead of testing every single value, we can pick a test point value, right? So up here, I usually put my test points. So negative 5 is to the left of negative 4. Between negative 4 and positive 1, we have 0. Between 1 and 3, we can pick the nice whole number 2. And after 3, we can pick 4. And we plug these test points into the factored version of the function, because we want to know what is the sign of this entire function. We want to know whether this entire function is greater than 0, whether it's positive. So we want the sign of x minus 3, x plus 4 squared, and 1 minus x. So we're going to have to plug each of these test points into the x's here. But let's try to make our lives a little bit easier and think about each of these factors for a second. So in particular, the one in the middle. So the factor in the middle, x plus 4 squared, it doesn't matter what I plug into it. It will always give me a positive number because I'm squaring it. So I really don't have to worry about plugging these test points into the middle term. It's just going to be a positive, and that's not going to affect anything. So I just have to plug the test points into the outer two factors, x minus 3 and 1 minus x. So negative 5 minus 3, that's a negative. Again, the middle term is always positive. So we can either ignore it or just always put a plus there. And then 1 minus negative 5, that's going to give me 1 plus 5, or 6, so that's another positive. So altogether, I have a negative interval. So I don't want that interval. I want, when is this whole thing positive? Greater than 0 means positive. So this first interval is negative. I don't want that one. Let's plug in 0. 0 minus 3, that's negative. Again, the middle part's always positive, don't have to think about that, and 1 minus 0 is positive. So again, I have a negative interval overall, which I don't want. So now we substitute in 2, so we get 2 minus 3, that's a negative. I said the middle is always positive, but now 1 minus 2, that's a negative 1. So altogether, I have a positive. So I have two negatives, they're going to cancel and give me a positive. So I do want this interval here between 1 and 3. Now I want to know when I'm greater than or equal to 0, right? So positive or equal to 0. So I want to include 1 and 3. So I'm going to have x is in the interval 1 to 3 with closed brackets around 1 and 3. And then let's check 4. So if I substitute in 4 minus 3, that's going to give me a positive. And then the middle is always positive, and 1 minus 4 is going to give me a negative. So overall, this interval is negative. So I do not want this last interval either. Now, there's one small thing that we have to make sure that we don't forget now, though. We wanted to know, when was I both positive or equal to 0? So in this interval from 1 to 3, I captured my zeros of 1 and 3 with these brackets. But this negative 4 value, that's also a place where the function equals 0. So I have to include this one value, negative 4. So what I'm going to do is I'm going to make space for it and say it's negative 4. I'm going to list that one value in curly braces and all of these values between 1 and 3, including 3. So that's kind of why I do also try to put a z above each 0 to just remind myself, oh yeah, there were more zeros. So as much as I'm canceling out these intervals in between, I still have to remember this 0 over here of negative 4. Now in this example, we're just asked to solve 4x cubed plus 4x squared minus 25x minus 25 is greater than 0. So we can use any method. So here, no matter what, we are going to have to find where this function equals 0, whether to put those zeros on a number line or on the x-axis to graph it. So we do need a factored form. And because we have 4 terms, we're going to go ahead and apply factor by grouping. So we can factor out a 4x squared, and we're left with x plus 1. We can factor out a negative 25, and we're left with x plus 1. We'll pull out the common factor, which is x plus 1. And we have a 4x squared left from the first term, and a minus 25 left from the second term. And now the quadratic is a difference of squares again. So 4x squared, that's 2x quantity squared, and then minus 5 squared. So we have x plus 1 times 2x minus 5 times 2x plus 5. When is that greater than 0? So we can either graph this now, so find the x-intercepts and graph it, or find the zeros and do a number line. So I would personally say, you know, they're probably equal, but I'm going to go ahead and just go with the number line because that's what most students struggle with at first, is the number line. So I'm going to go ahead and find all my zeros, which would be negative 1, positive 5 over 2, so adding the 5, dividing by 2, and then negative 5 over 2, subtracting the 5 and dividing by 2. So these are all of my zeros. I'm going to put them on a number line that goes from negative infinity to infinity, the domain. We'll plot negative 5 over 2 because that's negative 2.5, then negative 1, then positive 5 over 2. We will pick some test point values, so negative 2.5, to the left of that is negative 3. Oh, and then I forgot, these are zeros. Don't want to forget that. And we have negative 2.5 and negative 1, so in between that is negative 2. And then between a negative and a positive we have 0. And then greater than 2.5 we have 3. So we are plugging these test points into the function. So where is this function greater than 0? So that is positive, right? But again, the best thing to do is to use the factored version to substitute into. So we want to know the sign of the factored version. So x plus 1, 2x minus 5, 2x plus 5. Now there's no factor that we can eliminate here because none of these are squared. So we're just going to have to plug in these numbers into each factor. So negative 3 minus, negative 3 plus 1, we have a negative. Here we'd have negative 6 minus 5, so negative, and then negative 6 plus 5, so still negative. So overall, this is a negative times a negative, so a positive, but times a negative would give me a negative. When I plug in negative 2, we're going to get negative 2 plus 1, so that's a negative. Negative 2 times 2, that's negative 4 minus 5, negative. And then we'd have negative 2, so negative 4 plus 5, that is positive. So the two negatives cancel, give me a positive, times a positive, that's a positive overall. 0 is nice to plug in, because I'm going to get 0 plus 1, that's positive. 0 minus 5 is negative, 0 plus 5 is positive. So multiplying all this, I'd have a negative overall. And then when I substitute in 3, 3 plus 1 is positive. 2 times 3, 6 minus 5 is positive. And 2 times 3, 6 plus 5 is positive. So overall positive. All right, so let's go ahead and before we write up our answer, I mean, this isn't not too bad. We're just thinking about small arithmetic here to think about these signs. But if there's any shortcuts that we can use, I mean, it would benefit us. So one of the things I want to kind of tie this to is the concept of the multiplicity. So each of these factors had a multiplicity of 1. So even though we're not graphing it, we're doing it with a sign chart, we can take the concept of multiplicity and think about what that means. It means that we're going to cut through the x-axis. So let's say if I did a tiny graph real quick, and this is -5/2. Well, we were negative, we were below the x-axis, and if we have to cut through the x-axis, we're going to switch from negative below the x-axis to positive above the x-axis. So if the 0 comes from an odd multiplicity, that means my graph will have to cross the x-axis or cut through it and change sign. So we can see how they bounce between negative, positive, because every single factor had a multiplicity of 1. So at every 0, I'm going to have to change sign. So once I figured out the first one, sign of the interval was negative, I know I'm going to have to alternate. And that only works because the factors are odd multiplicity. Because if we have a factor that's even multiplicity, so now I'm just making something up. Let's say I have 2 and I know I bounce off the x-axis. Well, if I bounce off the x-axis, then the signs don't change. I'm negative and I stay negative. I'm below the x-axis and I stay below the x-axis. So those are just some of the shortcuts we can apply to when we use a sign chart. Now let's go ahead and finish this up. Now I wanted positive only intervals, so I want, circle this, I want everything but the first and third intervals. So in interval notation, I want everything from -5/2 to -1, and everything from +5/2 to infinity. And I'm using open parentheses because I want to know where my positive, not where my equal to these zeros. And that is my answer. Whoop.